Okay, well, given this wide range of materials that we might be interested in that might span everything from the viscosity of air to the viscosity of lava or the properties of blood or pancake syrup or any material like that, it's a very, very wide range of physical properties. And so it's worth spending a little bit of time thinking about what are the values and what are the properties that we're going to be interested in as fluid mechanics. So as engineers, we certainly value calculating accurate computed quantities. So we may be able to derive an analytic expression for a result, but we're going to want to put some numbers in, and we're going to want to make sure that we understand what the values are that we're going to get. So we certainly really want quantities that are going to be dimensionally consistent. We're going to need to develop some kind of physical intuition about what the right order of magnitude is. And to do that, then it's worth spending a little bit of time thinking about what the kind of material properties are that we're interested in. And so we'll take two prototypical materials that we're going to think about, and then we'll review a wider range of materials as well. So let's first of all think about one of the properties that we're going to be interested in, which is the density of the material. And we almost universally give that the symbol, the Greek symbol rho. So this would be reported in SI units in kilograms per meter cubed, and this would be spelled in English as rho. And so the density is something that varies over quite a wide range for materials. If we think about, for example, air, we've already seen that we would write the density, which is basically the number of molecules divided by the volume that we're in, is given by the equation of state for air, which would say that it's related to pressure divided by R times T. And for air at standard temperature and pressures, the density is about 1.2 kilograms per meter cubed. By comparison, if we think about water, so water, the density is about 1,000 times larger. So it's about 1,000 kilograms per meter cubed. And that's something that we probably all have a familiarity with, that we understand that when we hit water, if we dive in, it's dense. We don't really think much about the density of air. But another quantity that we're going to be very interested in fluid mechanics is viscosity. And this is something that frequently confuses people immensely. We don't really think about it. You walk through air every day, so it's going to exert some kind of viscous drag on you, but you really don't think about that for air. You certainly do when you try swimming, however. You understand that water exerts a friction on you. But it's something that we just really don't often think about what the magnitude is or the dimensions of this is, and it causes people a lot of confusion. So the symbol that we'll typically give for viscosity for a Newtonian fluid is mu. This is the Greek letter mu. And so this is the viscosity for a Newtonian fluid. We're only really going to be thinking about Newtonian fluids in the rest of this class. And the units of this is another thing that gives people frequently a lot of confusion, because it can be expressed in many different ways. And so one way of thinking about it is to express it as the units of pascals times seconds. And we already know that a pascal, which is a measure of pressure, is a Newton divided by a meter squared. Multiplied by a second, so you can also express it in Newton seconds per meter squared. But then you recognize that a Newton itself is a derived unit, and so you can also substitute that 1 Newton is equal to 1 kilogram mass times acceleration, so 1 kilogram times meter per second squared. And if I substitute for a Newton in here, you can see that I'll end up getting that this also comes out to have a kilogram, a meter divided by a meter squared, So that will just be a meter, and then it'll be a second divided by a second squared. So this will be a kilogram per meter second. A kilogram per meter second, and those are all the same, and they're all the units for viscosity. So if we look at this for air, then air, the viscosity of air is about 1.8 times 10 to the minus 5 kilograms per meter second at standard temperature and pressure. And that's why you never think about it. It's a very, very small value, and so we'll see that, in fact, that the drag that we get from walking through air is very, very small. If we deal with water, then for water, the viscosity is more appreciable, and the value is about 1.00. But the units, but the magnitude is 10 to the minus 3 kilograms per meter second. So you can see that that water has a much higher viscosity than air, for example. So that's why you experience a viscous drag as we go on. Now, as we move forward in this class, we'll see that, that there are combinations of these quantities that are also interesting to think about. And one that we'll particularly come across that we'll see sometimes is called the kinematic viscosity. So it's another measure of viscosity, and that's different than this quantity. So if we were being careful about this, people will frequently call this the dynamic viscosity. And the dynamic viscosity, you'll see, has units associated with dynamics or with force. It has newtons in it, even though you may not see it because it's been simplified into kilograms per meter second. Kinematics, on the other hand, is associated with just positions and accelerations of materials. And so the kinematic viscosity for a fluid is given by the Greek variable nu, which we can write like this. And we have to be very careful when we write this. This is not a velocity. This is a Greek variable nu. And it's defined, so it's equal to, by definition, to mu divided by rho. So we can ask, what are the units of this? And so if we just combine what we have over here, we have kilograms per meter second for the units of viscosity, and kilograms per meter cubed. And so this ends up having the units at the end of the day of the kilograms cancel of just meters squared per second. And that's why we call it a kinematic viscosity, because it has no force or no measures of force in here. And you might have seen things with units of meters squared per second before. This is what people will frequently refer to as a diffusivity. So all diffusivities are a measure of how much something spreads through something in terms of an area per time, so in meters squared per second. And in this case, we can ask a question as we might ask, what is diffusing? And we'll show as we go on in this class that, in fact, what we're thinking about when we consider nu is the idea of momentum diffusivity. That if I stir a material, there may be a region of high momentum and a region of low momentum, and this property is a measure of how fast material can transport momentum. And so the kinematic viscosity will show up this way. And here's where there's a surprise. So we could calculate the kinematic viscosity for air, taking the information that we have from the density and the viscosity. So if we take mu over rho and we evaluate it for air, then the number that we get is something like about 1.6 times 10 to the minus 5 meters squared per second. By taking this value and dividing it by that value. But if we evaluate the kinematic viscosity of water, and we again calculate this, then now we have a viscosity that's maybe a factor of 100 higher, but we're dividing it by a density that's almost a factor of 1,000 higher. And so this comes out to be closer to 10 to the minus 6 meters squared per second. So in some sense, water is less viscous than air, but only when we think about it in terms of this measure of the kinematic viscosity. And we'll see that that's very important when we try and understand this idea of diffusion of momentum. A final thing to point out while we've got all of this information on the board is that these numbers can be very, very small. So we see lots of 10 to the minus 5s around here. And so frequently you'll see yet another set of units that people will use, which is what people call CGS units, for centimeters, grams, and seconds. And so it's worth us just making a quick note of that in CGS units, then the unit that is typically used to do this is called the poise. This is named after a French scientist, Poisset, who we'll see as we go along. And the number that we need to know is that 10 to the minus 3 kilograms per meter second is the same as 1/100th or 1/10th of a poise. So 10 to the minus 3, like that is can be expressed as 1 centipoise. And so you'll sometimes see people will refer to viscosity in centipoise. So that's for dynamic viscosity. We have the same issue when we come to think about kinematic viscosity. And here in CGS, people will often talk about units in terms of Stokes, or again, sometimes centistokes. And here what we'll find is that 1 centistoke is equal to, of course, 0.01 Stokes, which is equal to 10 to the minus 3 meters squared per second. So you'll sometimes see people refer to kinematic viscosities in terms of centistokes as well.